We tried to kill a tardigrade. For the past 250 years, the human scientific community has been trying to kill tardigrades. This is the record of those attempts. Some of the attempts were intentional, framed as experiments. Some were accidental. Most failed. A few succeeded, and the ones that succeeded taught us something more interesting than the popular internet claim that these animals are indestructible. They are not. This is the log. In the autumn of 1773, a German theologian named Johann August Ephraim Goethe placed a drop of pond water under a microscope. He saw an animal that looked like a translucent gummy bear with 8 stubby legs walking slowly through the field of view. He named it Kleiner Wasserbär, German for little water bear. This is the first written record of a tardigrade. Goethe was not trying to kill it. He was trying to describe it, but the documentation matters because every later experiment on this animal traces back to this moment. He noted the body shape, the 8 legs with claws, the slow walking gait. He sketched it. What Goetze did not yet know was that the animal in his drop of water was capable of doing something almost no other animal on Earth can do. He did not know it because he did not yet try to dry it out. That experiment would come 3 years later, conducted by an Italian Catholic priest who was, at the time, one of the most aggressive experimenters on small animals in Europe. Lazzaro Spallanzani was a biologist and Catholic priest who specialized in experiments that, by modern ethical standards, would be difficult to get approved. In 1776, he obtained tardigrades from sediment in rain gutters and subjected them to a procedure that any reasonable person would expect to be lethal. He dried them out completely. He let them sit, fully dehydrated, as small crumpled brown specks on glass slides. He left them that way for an extended period. Then he added water. The tardigrades came back to life. Within minutes of rehydration, they uncurled, extended their legs, and resumed walking. Spallanzani gave them the scientific name they still carry, tardigrada, meaning slow steppers, and published the result. The scientific community at the time did not entirely believe him. What he had documented, although neither he nor anyone else at the time had a word for it, was cryptobiosis. The tardigrade, sensing that its environment was running out of water, had expelled approximately 97% of the water in its body, curled into a small dehydrated shape called a ton, and dropped its metabolism to roughly 1/10,000th of normal. In this state, it was, by every measurable standard, not biologically alive. But it was also not dead. It was, biologically, paused. This was the first successful resistance to a killing attempt. It would be repeated in essentially every experiment for the next 250 years. In the early 1920s, researchers began testing the limits of cryptobiosis with longer dehydration intervals. How long could a tardigrade stay dry and still come back? A tardigrade was dried, sealed in moss, and stored. Years later, water was added. The tardigrade revived. The interval kept being extended. Months, years, decades. In each case, the revival success rate dropped, but a meaningful percentage of specimens always came back. The current well-documented record for verified revival is around 30 years, when specimens are kept frozen in moss, a related state called cryobiosis. There are older claims, some of them historic, including one 19th century report of revival from a herbarium specimen over 100 years old, but those are debated. 30 years in frozen moss is, however, an established fact. A tardigrade that was frozen in 1995 could be thawed and rehydrated today and would, with reasonable probability, start walking. This was the second confirmed failure of attempts to kill the tardigrade through time alone. We could not wait it out. In September of 2007, the European Space Agency loaded approximately 3,000 tardigrades onto the Photon M3 spacecraft. The animals were placed on the outside of the craft, where they would be directly exposed to the open vacuum of space, the temperature swings of low Earth orbit, and the full spectrum of solar radiation. The exposure lasted 12 days. The principal investigator was Ingemar Jansson at Sweden's Kristianstad University. The goal of the experiment was specifically to test the limits of cryptobiosis under conditions no living tissue had ever survived in an uncontrolled way. The vacuum did not kill them. The samples protected from solar ultraviolet radiation came back at a survival rate of approximately 68%. Of those, many laid viable eggs after revival. The vacuum alone was not lethal. The combined exposure to vacuum and full unfiltered solar ultraviolet radiation, however, was. Survival rates dropped to single digits. Of the Milnesium tardigradum specimens exposed to the full radiation, only 3 individuals survived. This was the first attempt to kill a tardigrade by removing its environment entirely. The tardigrade had no environment to lose because it was in cryptobiosis. The body was not relying on atmospheric pressure or external water. It was not consuming oxygen. The radiation, however, did damage DNA at a rate the tardigrade could not entirely repair, and that was where mortality came from. We had found a kill mechanism. It just required combining open vacuum, hard ultraviolet, and 12 days. Following the Photon M3 results, multiple labs ran controlled radiation experiments on cryptobiotic and active tardigrades. The findings were consistent. Tardigrades in cryptobiosis can survive gamma radiation doses on the order of 1,000 grays, which is approximately 1,000 times the dose that would kill a human. Active hydrated tardigrades are significantly more vulnerable, surviving around 100 to 200 grays. The difference is not subtle. The same animal can withstand a 1,000-fold higher radiation dose if it has been dehydrated first. In 2016, a team at the University of Tokyo, led by Takuma Hashimoto and Takekazu Kunieda, identified the reason. Tardigrades have a unique protein called D-sup, short for damage suppressor, that physically binds to their DNA and shields it from radiation-induced breaks. The D-sup protein has since been inserted into human cells in laboratory settings, where it provided measurable radiation protection. Radiation by itself in the cryptobiotic state does not kill tardigrades quickly enough to count as a successful attempt. Through time alone, we cannot wait them out. Through radiation alone, we cannot break them. In April of 2019, an Israeli spacecraft called Bereshit attempted to land on the moon. It crashed. The spacecraft was carrying, among other items, a payload prepared by the Arch Mission Foundation. The payload included samples of human DNA, 25 million pages of text encoded into thin nickel sheets, and large numbers of dehydrated tardigrades. The lander struck the lunar surface at roughly 500 kilometers per hour. The Arch payload was not designed to survive that impact intact. The tardigrades, however, were already in cryptobiosis when launched. It is not currently confirmed whether any of those tardigrades survived. They almost certainly did not revive on the lunar surface. The moon has no water for rehydration. But whether they were destroyed by the impact itself, or whether they are currently sitting dehydrated on the moon, waiting for an event that will not come, is unknown. This is the first known unintentional attempt to kill tardigrades by crashing them into another celestial body. It probably worked. Probably. The most recent and most useful findings have come from studying tardigrades when they are not in cryptobiosis. When a tardigrade is active and hydrated, it is a small, soft-bodied invertebrate. It can be eaten by nematodes, it can be eaten by larger predatory tardigrades, it can be eaten by mites, by some aquatic insects, and by various microscopic fungi that consume it from the inside. It can be killed by sustained heat. Not the brief moments of high temperature it survives in cryptobiosis, but minutes-long exposure to boiling water in the active state. Most active tardigrades die at sustained temperatures above 40 degrees Celsius. It can be killed by chemical solvents that damage cell membranes. It can be killed by drying it too fast for it to enter cryptobiosis. The dehydration process takes minutes to hours. If the tardigrade is removed from water faster than that, it dies dehydrated before entering the ton state. The popular claim is that tardigrades are indestructible. The log, read carefully, says something more specific. Tardigrades have one technique. The technique is to stop being biologically alive when conditions are bad and to start again when conditions are good. The technique works against vacuum, radiation, temperature extremes, pressure extremes, and time itself. The technique does not work against fast environmental changes, against predators in the active state, or against soap. The tardigrade is not the indestructible animal. The tardigrade is the animal that figured out how to surrender without dying. We have been trying to kill tardigrades for 250 years. We have mostly failed. The ones we managed to kill, we killed by attacking them while they were paying attention. If you watched all the way through, hit subscribe. Next week, the parasite that becomes a tongue.